And now we have used the phase diagram to understand the structure formation during solidification of binary eutectic alloys. We have looked at the primary precipitation, and we have looked at precipitation in the two-phase region and the eutectic precipitation. We will now turn to the steel system. And steel is the system with iron and carbon. So we're going to look at the iron-carbon phase diagram and how it can be applied during transformations in that system. Now we will mostly focus on the transformations in the solid. So first we start to look at the simple iron system. Here we see the phase diagram for pure iron, but this is a single line as it is a one-component system. And what we can see is the different transformations or the phases that are stable in certain intervals in iron. And if we start at high temperatures here, where we have a liquid, and we see the melting point is 1536 degrees centigrade. And first we get a delta ferrite phase, which is stable down to 1395 degrees. Then we have the austenite phase, or the gamma phase, stable in this interval from 911 up to 1395. And then at lower temperatures we have the alpha phase, or the alpha ferrite phase, stable from 911 down to room temperature. We will mostly deal with this transformation in the continuing. The solidification part of the system we will leave apart from the beginning, and it's actually mostly important for stainless steels and alloys like that, but for understanding the regular structures in steel, we will focus on this part. So now we will see what happens when we end the carbon and get the iron-carbon system. So here we have the iron-carbon system, which will be the base for the discussions in the common pictures. And here we can recognize the line here we just looked at for the pure iron, the melting and the transformation to austenite and the transformation to ferrite. But we see here what happens when we go into the carbon side of the system. Normal steels have maybe up to a little bit more than 1% carbon, so we are going to deal with mostly this interval of carbon concentrations. And what we see first here is when we look at the austenite area, is the one-phase austenite, that when carbon increases, we will see that the area here, the temperature in which austenite is stable, is increasing. It means that austenite exists in a longer temperature interval at higher carbon content, and we say that carbon is stabilizing the austenite phase. Austenite can put in carbon atoms in the crystallographic matrix in an efficient way. But if you look down here, we see ferrite. That's the opposite. The crystal structure in ferrite, with its body-centered cubic, cannot dissolve much carbon. Actually, the maximum solvability of carbon is 0.022, and it occurs here. It's even smaller at other temperatures. So here we cannot put in so much carbon, and that's a very important thing here, how carbon is distributed between the austenite and ferrite during the different transformations occurring in this region. If you look in the system as a whole, we see that we also have an eutectic point here. When we come to concentrations of carbon over 2%, we say that we get cast iron instead. So steels are in this region and cast irons are up here. And you see that when we have a composition here, we will start to solidify with austenite, and then we will end with this eutectic. We will not talk about the cast iron in this course. We only need to remember that it's a cast iron when we get something of this eutectic in the structure. An important feature here is also the cementite phase. It's a compound, Fe3C, which then has 6.7% carbon in this compound, positioned here. And it's important as it is one part of this two-phase region. This two-phase region with ferrite and cementite. And therefore cementite is an important phase in the structures formed in this region, in the regular steel structures. So let's start now to focus on this part only and look at some transformations occurring here.